speak. And if you, this is what we achieve today typically. So if you have a brand new Volvo V60, 2017 year model diesel engine, you are at this level roughly. If you drive an electric car in Sweden, you're maybe down here somewhere, but in most of the world, because the electricity is not clean, most of the electric cars are around diesel type car territory really. And if we would make a life cycle analysis, we would actually see that an electric car would in many cases be much worse than running on diesel. But there is a high potential in doing something else. And what we want to do and what we're discussing today is the renewable fuels. So if you take this car that is already existing and you run it on HVO, and it says frityrolja here, so this is cooking oil. So it's waste cooking oil. And it's a limited resource, so we cannot do that on all cars, but we can run on HVO. And with this machine that doesn't cost more than it, I mean, it's standard equipment. You can directly make a huge benefit. It's more than a 90% reduction here on the CO2 emissions. And we can actually achieve even better with electric drive in the future. If we have clean electricity, we can run the electric cars and vehicles with almost zero emissions of CO2. And also the problematic production of batteries today. I mean, if you have clean electricity for production of batteries in the future, those will also be of low greenhouse gas impact. Like I said, HVO is maybe not sufficient. We need to have more fuels. And I put it in some figures here with methanol. So this is what you can do with methanol. And if you combine electric drive with methanol engines. So hybridization can be quite good actually to do. And this is the challenge, just to give you an idea how difficult it is. This is the Niagara Falls. And you have 2/3 behind here, and you have 1/3 here. You can see people here. And the amount of water that is flowing here is roughly equivalent to the amount of oil that we are pumping up from the ground continuously. It's amazing, isn't it? We're going to replace that with clean electricity and renewable fuels. And we don't have either of them today on enough scale. So looking at the production of electricity, we see it's mainly coal-based and natural gas. And we see a lot of hope actually in the development of the solar energy, but the energy increase in the world is very strong also. So maybe we'll just keep that and add more solar production. And there's also discussion about replacing nuclear. So how are we going to do that? So I think it's very important that we do everything we can. We do all the best we can with electrification. And we do all the best we can with renewable fuels and do it in parallel. Because if we focus on one thing, then we will not change the world into a sustainable world. The good thing is that we don't need to replace all the fossil fuels with renewable fuels. You can see this is the study from Thomas B. Johansson, the Fossil-Free Road Transportation Investigations in 2013. And this is the current situation, more or less. We have a lot of fossil energy in the transportation sector. This is the road transportation sector. But you can see there's a large improvements. So better vehicles, different patterns of travel and so on, that reduces the energy requirement in transportation. And the remaining part, you can see that we have roughly 25 terawatt hour here of renewable fuels. And electrification becomes more and more important over time. So we maybe need 30% of the fossil fuels that we're using today. We need the same, or 30% in renewable fuels, so to speak, for the future. And I think this is one of the main issues with renewable fuels. We have so many options. So if we would only have one option, I'm sure we would have been using that quite a lot today, much more than we are using all the different variations we have. So it is challenging, of course. We're always discussing which is the best and which is the worst. So. Cost is very important, of course. That what matters, I think, to many people. And we have this great study from, as I wrote Maria Gran here, but it's our team, but it's Brunolf, if you want a publication. And they looked into a lot of different publications to find what are the costs in the future for different fuels. And we have the fossil fuels in red here right now, and you see it's a big span. It's a number of different investigations, but there's also a different span of what you can estimate for the future. I mean, no one can really be really sure about how it will be in the future. So then we have the lignocellulose type fuels. Methanol is one of those, and it seems that they are in a more narrow span, so could be cost effective. And if we look into the electrofuels, if you have excess electricity from, for instance, wind or solar, you can produce fuels. Don't just shut it down. Use it to produce fuels instead. And then we get fuels to the cost around, they think, 100 euro per megawatt hour. So how much is that? Is that good or bad, or what do you say? 100 euro per megawatt hour. So how much is that? Do you know? Thanks.
I think it's good.
Yeah.
I think it's affordable.
Yeah, I converted it to something else. So 40 euro cents, roughly, if I made a correct calculation here, per liter of gasoline equivalent energy. And gasoline and diesel today is around 25 to 40, so I mean it's probably not a catastrophe if we go for the renewable fuels in the future from solar and wind and carbon sources. So nice with some cost comparisons. What if we replace all Sweden's cars with battery electric cars? So just the bonus price for the batteries is 846 billion Swedish crowns. So that's quite expensive. We can compare that with the high-speed train system in Sweden, 250 billion Swedish crowns. That's lower cost, still very expensive, and to quite few people, I would say, that can use that system. So electric roads, I think electric drive should use direct connection with the production of electricity as much as you can. And Mats Allakil is a researcher in Lund, he also works at Volvo, and he estimated that the electric road net for Sweden would cost 150 billion Swedish crowns, and we can use a lot of vehicles for that, and then we need batteries or kind of small combustion engines to take us in between the nodes of this road system. That would be very effective. Biomethanol production plants in Sweden, we can have them in 5 years' time if we decide to do it today. And 30 terawatt hour, that would cover the needs for the road and for the sea transportation we have in Sweden. The investment is 65 billion Swedish crowns. Of course, you still need to pay for the fuel that is produced in the end, but that's the investment. And we can compare that with the Swedish annual oil import of 103 billion Swedish crowns. So what are we going to do in the future? Are we going to keep the money to ourselves, have our own production, putting people to work, or are we going to export this money to, well, Norway is a decent country, I would say, but there are some that are maybe not that democratically into the oil business, or what do you think? Yeah. Why are we sponsoring them? I don't understand that. Sorry.
I think we should make the pro.
Yeah, then we have this very strange thing, global subvention of fossil fuels. That is an astounding 3,500 billion Swedish crowns. I don't understand why, but that's the way it is. So is methanol a good engine fuel? Yes, it's been used for a very long time in racing application. In war machinery, you could double the power output of an engine with methanol. I'm going to be very technical here, but thank you guys for explaining how combustion engine works to the audience here before, so, because I will show some things and it's maybe difficult to understand. So what we have on this scale here is fuel reactivity, and gasoline engines or methanol type fuel, they are low reactivity fuel. They are difficult to ignite in a combustion engine. So you use a spark plug. And this is the traditional gasoline engine where you introduce fuel and air. It's pre-mixed, and then you can see it's kind of homogeneous here, and then you ignite it with the spark. The diesel engine process, there you need a fuel with high reactivity. It's very easy to ignite. So you introduce air to the engine, you compress it, it gets warm, high pressure. Then you introduce the fuel, and then it starts to burn immediately. So completely different ways, but that's the way the traditional engine works. What we have been doing in Lund for many years now is doing something in between the diesel process and some sort of homogeneous process. So we inject the fuel with the injector inside the combustion chamber, but very late in the process. But still together with this fuel that is having, very high resistance against ignition, gives us a mixing time And so we get quite some benefits from that. And there are some other concepts you can do as well, combining two fuels. Some call it RCCI. You can call it dual fuel as well, and that's been proposed for different applications. And the summer project looks into this with alcohol fuels, where you use an ignition improver. The methanol project I represent here is working on this mainly, and then we have the Stena Germanica process, where they were very intelligent and combined the good things with dual fuel and having double direct injection of both fuels, so getting away from some of the problems. What we also been doing in the summer project down in Lund is combining this concept, the conventional gasoline engine, with the PPC concept, so late injection and spark ignition. So, Joanna, I have to ask you, how about the time?
Yes, you should be coming to an end.
I should be coming to an end.
Yes.
Okay, I felt it.
So we have time for some questions.
Absolutely. So what I will do directly is I will jump to the end here. It was a lot of materials. I was not sure what I was going to show you, but what we can achieve, at least with this different concept, is so a bit busy slide again. So this is the efficiency of an engine. Here is how much soot you produce. So you want to be up here. And the best diesel engines of today, they are over here. They produce soot, and the efficiency is pretty good. But if you use alcohol in this type of diesel engines, so the way they warn you to do, but we do it anyway, then you get very, very high efficiency from the engine and no soot emissions. And also other regulated emissions, you can see it with methanol PPC, we are down very close to the conventional gasoline engine with the three-way catalyst. And if you tune the three-way catalyst to your engine very properly, the amount of emissions you get hydrocarbon emissions that equivalent for 20,000 kilometers of driving the same amount as 1 liter of washer fluid for the window. So that's the amount of hydrocarbons you get from an engine if you do it right. There's quite some challenges with methanol. I think we can come back to those later. Some conclusions. Methanol can be produced at low cost from various sources. It's compatible with gasoline, ethanol, and butanol. I think that's very important because now you're lowering down the number of engine calibrations you need if you have a sort of a mixed fuel system. Excellent greenhouse gas potential, toxic to humans and corrosive. Those are the challenges, I would say. Reduced impact from spills is good. Engine performance, methanol PPC possible with more than 54% indicated efficiency. So methanol engines can be much more effective and cleaner than the best conventional engines we have today, if we do it right. Similar larger loader as conventional engines, stratified DI-SI is possible and can be a game changer. Emissions, we have managed to do Euro 6 compliant without emission after treatment system. There is no soot, but we can have very small particulates that we need to think about for the future. And with this modern concept, we can avoid formaldehyde emissions and insulated corrosion altogether. Okay, thank you.
I say we still give the chance for 1 or 2 very short questions. Someone has, even though you got 2 applause already. Does anyone have a question for Martin that you can't wait to pose? It was all crystal clear. Perfect.
Yeah. Okay, thank you.
Then we give you a third hand. Now we will move on, and in the time when Julia will get her headset, I will introduce her. So now we will move away from the engines on a more systems perspective, and we have Julia Hansson, associate both to Chalmers University of Technology and to IVL, the Environmental Institute of Sweden. And she will talk about prospects for renewable marine fuels. And this is a project which has partly been financed, as I said, by F3 and the Swedish Energy Agency within the program that we have together, which is called Renewable Fuels and Systems. And I will give the floor to Julia just when she's finished, but for those of you that are interested, we will have a conference within this research program the 25th and 26th of October, where all the 29 projects within the program will be presented, and it's open for everyone. So if you sign up to our newsletter, you will get an invite and you can sign on.
Okay, vi testar här.
Funkar?
Okay, no. Yes, thank you very much for that nice presentation of me. Yes, I will present part of a project, or the initial part of a project that is ongoing, as Ivana just told you. And it's a joint project between IVL and Chalmers, as she said. But also this research that we're doing here about shipping and the impact on the fuels, we're also doing, we'll continue doing part of it also with another project that is called SHIFT, Sustainable Horizons in Future Transport, which is a Nordic project. I was just, and we also have a web page for that project, so I thought if you're interested in following what we're doing, we will also distribute it via this project and continue it there. Well, and the background, as Martin already said, of course, there are a range of different options. Also, if you look only on the marine sector, which is, of course, the challenge in this area. I've been working quite a lot with the biofuels for the transport sector in many years, and of course, it's now addressing the shipping sector. Of course, there are quite a lot of the challenges are the same, but also the marine fuels, of course, have some specific. Or are unique in some ways, of course. But we don't have to go into all this. But of course, then also the short background to the project. I mean, you can compare different fuel options in many ways. You can compare it, as you saw before, well to wheel. For example, looking at this life cycle perspective on the greenhouse gas emissions, and you can also make a full life cycle analysis looking at the environmental impacts. But of course, when you look at making fuel choices, you're also very interested in a range of different factors or criteria, you could say. Some that are more technical, related to the technical, as we were in before, like fuel properties, etc., and engine possibilities and engine how they work. But also related to economic aspects, of course, related to price. And price for investments, or price for the fuel and operational costs, for example. But it could also then, as I said, it would be environmental cost, and of course not only greenhouse gas emissions, there are of course a range of other aspects there as well. NOx and SOx and health aspects, of course. And also other social aspects more related kind of to policies, for example, and regulations, etc. And the aim in this project is more to address it from a rather broad perspective, trying to consider a range of different criteria. And comparing it. And the result we will present here is, as I said, initial findings in this project that is ongoing and that will continue for the rest of the year at least. It's part of it is presented in the master thesis that has been completed as of this morning actually. So they are very new results, and we will work further with them in the project. So I might come back and get another presentation later where we have finalized the full project. So I will present what is called an initial results from what is called a multi-criteria decision analysis of alternative fuels for the marine sector. And I will introduce this approach, this multi-criteria decision analysis. But also I could say that the project is also about testing this approach and trying to see what it can provide with or contribute with when you do this kind of analysis, and then looking at the shipping sector. And as I said, then we look not only on environmental aspects, we try to include a range of different aspects for that. So then, as we're formulated, the overall aim of this part of the project is to assess the prospects of renewable fuels in the shipping sector by conducting a multi-criteria decision analysis of selected alternative fuels with a panel of shipping sector-related stakeholders, using them in this analysis. And the multi-criteria decision analysis specifically used for this project is called analytic hierarchy process. And what should be kept in mind also is that the time perspective in this study is said to be 2030 in order to look into the future, to say what when the stakeholders value different things, put weight on different aspects, they should have the future in mind and not only the current situation, which also have a very big impact on the outcome, of course, which you will see. So what we are addressing, you could say that there's 3 different things that we are addressing, or that Stina Monson, who were doing the thesis, that she addressed in the thesis so far. And that's partly looking at the relative economic, technical, environmental and social impacts of the selected alternative marine fuels. And then we also consider the relative importance of different criteria in the selection of alternative marine fuels according to the stakeholders. And then the outcome, or the final outcome actually, is answering the question of what alternative marine fuel is most preferable considering the stakeholders' preferences. So there will be a ranking of the different options that we have included so far. And yet, in order to start this analysis and project, we thought it would be a great opportunity to have a master thesis student working on this. And in order for her to be able to finalize that time, we had to limit the amount of options, of course. So then we decided to include liquefied natural gas and methanol produced from natural gas and methanol produced from biomass. But also, since we looked into the future, include hydrogen from electrolysis by wind power as an also renewable option in the future than using fuel cells. But of course, when we continue with this project, we will include even more options, of course. And we also decided to have a limited amount of criteria, of course, but all covering then all different sustainability perspectives. So we ended up with 10 criteria, and these were selected together with the reference group of the project in order to be sure that we kind of include those that they consider most important, or most from their perspective at present. So then, what is multi-criteria decision analysis? Well, it is a tool for managing very complex decision problems. And what you do is that you score the alternatives and you can weight the different criteria. So in this case, the alternative marine fuels will be ranked based partly on how they perform with respect to the selected criteria. For example, how they what costs they have for fuel and for investments, and also, for example, for greenhouse gas emissions, how they contribute to that, or other environmental aspects. And also the relative importance of the criteria. And as I said, that's where the stakeholders are part of the project. And also this multi-criteria decision analysis approach, then it's possible to consider differing views, that people have different opinions on how they value different aspects, which also is part of the projects. So then, saying something about which criteria that we included so far, this is some sort of approach figure. As I said, we looked at both economic, technical, environmental and social aspects, and related to economic, we looked at fuel prices, operation cost, investment cost, and propulsion. Technical aspects included available infrastructure, reliable supply of fuel, and environmental aspects, acidification, climate change, and health impact. And related to social, we included safety issues and upcoming legislation. And of course, the good thing with a multi-criteria decision analysis is that it is possible to include then aspects or criteria that have different units, for example, that some could be expressed in economical terms, for example, then euro per megajoule, while other could be expressed in completely different units. And it can also be so that even though if you can't really quantify them, if you can quantify them by saying that this is higher than the other one, that's also possible to consider in this model and to make it in a mathematical way. So it's sort of a mathematical approach in the end. But what you do then? Well, you kind of start by getting the data for the different criteria that you included, see what else in the literature about costs and environmental aspects, etc. And then you make pairwise comparison between the different options that you have in order to kind of rank them to see what's the highest and the lowest impact for them. So then they are scored based on how they perform with regard to the specific sub-criteria. For example, then related to the fuel cost, for example. And at the second stage, you put weights on the criteria based on how important they are. And in this case, this was done on the stakeholder workshop, where they weight the different aspects. And then you can end up in the ranking of the fuels as a final outcome. And if you look at the first, then the scoring of alternative marine fuels, when we only looked at the literature about what is available in terms of costs and technical aspects and etc. for all the criteria. Then Stina found that when she looked at the literature, what she could collect in this project, she found that LNG was best, or was then the best in fuel prices. I mean, that means that it has the lowest fuel price. Also that this has the highest available infrastructure. And methanol from natural gas and methanol from biomass, both were best in investment cost and operational cost and safety, meaning that they had the lowest than investment cost and operational cost, for example. While hydrogen were considered the best in relation to reliable supply of fuel, acidification, climate change, health impact, and upcoming legislation. But then I will go to the stakeholder workshop and the different values that the stakeholder had. There's actually some of you that were at that stakeholder workshop providing input. So then the workshop, they were asked to then value the different criteria. And then they were not really considering the specific fuels, they were considering the different criteria solidly, which means that this could actually be used for other things as well, even though we said that this should be directed to fuel choices. So then they considered these criteria wise. It means that they consider them the economic aspect of criteria to be the most important, followed by social, environmental, and technical issues at least. And also if you look into the sub-criteria related to economic, it was fuel price that was considered most important. And also if we then ending up with the final result from this this task. Well, in this case, all the stakeholder persons at the workshop, they filled in this, or they made this variation on their own individually, but then we merged this into one joint outcome. And then the ranking was as follows. Well, high value then means that it's the most preferred option. So then hydrogen turned out as the most preferred option, followed by methanol and LNG, which was almost equally preferred in that sense. But of course, the relation is of course sensitive to changes in criteria weights and perspective used in the scoring. But also, besides having this individual ranking, we also asked the group to sit in groups and try to have a role play, acting as authority, some of them, and some acted as ship owner, and tried to weight the different aspects, considering that they were authority representatives or ship owner representatives. And then we ended up with a somewhat different criteria weights. The authority, when looking at it from that perspective, were being representative of the authority. Environmental and social aspect were considered highest, and for ship owners, the economic was considered highest. Not so very unexpected. But this then, turning it into the ranking of the fuels, this indicated that in the case of authorities, hydrogen was the most preferred option, followed by biomethanol, but for the ship owners, liquefied natural gas, followed by methanol from natural gas, was considered the most preferred fuel option. And also we had two other role play down, but we will not need to go into that. Looking at the fuel and engine manufacturer, but we can skip that result today. And also I thought before I end up, it's of course very interesting to know which stakeholders that were involved, because of course since it's been impacting or influencing the result very much. So besides some researchers that we had in the end, we also had some persons from Stena Line, Wallenius, Wärtsilä, Dream, the Swedish Maritime Administration, Swedish Transport Administration, Energigas, and SSPM contributing to this work. But then to finalize some conclusions and findings so far. Well, of course, the results, when you do this comparison of different options, of course, it depends on which alternative marine fuels that you include. And our aim in this project is, of course, to include some more biomass-based or renewable-based options in order to see how they perform compared to the others. And also it depends, of course, which criteria that you include. I mean, we decided to have 10 criteria. Of course, there are most likely 15 or 20 that we had from the beginning that could be included, which of course also could alter the outcome. And also, of course, this data collection on the different aspects. We will continue with that as well, and making sure that we actually have the right relative comparison of data there for the different options. And also the mix of stakeholders, of course. I mean, if you had done the same exercise, perhaps the outcome would have been somewhat different. So before finalizing this, we will also make more sensitivity analysis in order to see how that will influence the result of the final outcome. Yeah, that's that.
Thank you. Do we have any questions for Julia regarding this?
Do you think it's a problem to present results like this when it's so dependent on the input, on the stakeholder mix, for example? Because all the publications are subject to abuse, or to someone is grabbing the information out of context. I mean, because here you expose yourself to people using these numbers in completely their own ways.
Yes, I think that's a general problem, but also I have felt when doing this earlier on that it's generally also good to present it, because then you get a lot of feedback, which means that you can improve the results. And also, especially when you make the written publication, which is where people mainly use your stuff, where they can actually use it for. And there you can be very more also clear about saying that this is initial findings, very much based on this aspect, for example, the stakeholder mix, for example. More also specific saying what conclusions can actually be drawn. And then if someone wants to use it for something else, then you can never make sure they cannot misuse it. But at least you can do your best in trying to explain how it should be used and what you can actually say, what are the uncertainties, etc. So
if you do ranking, someone will just grab the ranking without looking into the background.
Yeah. So yeah, exactly. So therefore, when we do it in more written publications, then we are more like perhaps not always presenting the ranking in a very specific way. Perhaps you only write it, not perhaps. Generally, the way is not putting it in a figure, because figure are more easily to use than if you have it in a text somewhere where you have to at least you have to read the text very carefully before you can use it. So we usually think about those things more. But just presenting it in this way at oral presentation, I think usually is very good, because if you're at least allowed to say that these are certain results, initial findings, there could still be changes in them, then I feel that people tend not to misuse them.
And you stir up the discussion.
Exactly, and you get more input, making sure that you can have a better outcome in the end. So.
I actually have just a different angle of that question that I will give to you while you take mine. And you were asking how can you present results without people misusing them, and I would like to ask, but this type of results, because it's not like measurements, it's more so in a way towards social side results. What's the aim of the results? How do you want to use the results? What's the purpose, the overall purpose of the study besides generating results?
Yeah, well, in this case, I think it's learn more about how people value different aspects and how important that is for the outcome. I mean, when you are trying to convince people to use a specific fuel, for example, or more methanol going into investments, if you have more knowledge about these factors that they think are important, then perhaps it's easy for you to know what you should try to explain for them and try to make more specific for them. If you're trying to get them engaged in projects or get funding for projects or funding for specific investments. I mean, if you understand more how they think, I think it's easy for you to kind of get the project going. So that's, I would say, in this case, that's our aim of using this methodology, which is where you can get the stakeholders to actually put values on how they think. So.
Do we have an additional question to Julia? No, you will have the opportunity during the coffee. Thank you very much. Then we have the third presentation in this afternoon, and it's just before coffee, but now we are on time again, so now we don't have any issues with that. And I will give the floor to Magnus Lundqvist, and he's from Reactivity, where he's the project manager of not just one, but two projects that you will incorporate into one presentation with interesting results for us.
Yeah,
go ahead.
This is the first time I give a presentation with an ocean view, so I don't know really where to focus here. It's a really nice setting here. So, I come from the steel industry, and I represent Reactivity, which in this picture is this part and this part. So this is an industrial site about 3 kilometers outside the city center of Luleå. The rest that you see here is SSAB steel plant in Luleå. They produce 2.4 million tons of steel per year. I don't know much about methanol, and I know absolutely nothing about shipping, but I will try to explain why I ended up with a project where we aim to produce methanol for shipping. I will do my best. Better? Yeah, so the steel industry, they have a big challenge. The ore-based steel production is very dependent on fossil coal as a reductant and as a fuel. And you see an example here of the steel making process. They bring in ore. In Sweden, it's LKAB ore from Malmberget. And they bring in coal that they use for injection into a blast furnace and as coke also injected into the blast furnace. If we take SSAB Luleå, for example, for producing 2.4 million tons of steel, they need more than 1 million ton of coal per year. So it's huge amounts. The other process steps is they remove sulfur. It's removal of coal. So this is where we go from iron to steel. There is some addition of alloying elements, and it's continuous casting. SSAB Luleå emits 3 million tons of CO2 per year, which is the biggest point source in Sweden. Even though SSAB, they are one of the most efficient steel producers in the world, but the nature of the process is such that you will have CO2 emissions when you produce iron from iron ore. Most of the emissions come from the blast furnace, at least 70%, in many cases more. And if we once again look at SSAB in Luleå, for example, the blast furnace produced 270,000 normal cubic meters per hour of blast furnace gas. And today this is mainly used in the power plant to produce electricity, district heating and steam. A blast furnace gas composition for a Swedish blast furnace plant is typically 20% CO, 4 or 5% hydrogen, and the rest is inert, CO2 and nitrogen. So it's a very lean gas. There are two ways to significantly reduce the CO2 footprint for ore-based iron making. One is fuel switching, which means that we partly or fully replace the fossil fuel. In Sweden, biomass is one option. In many other countries, it's not possible at all. Electrification is another option, and maybe you have heard about the hybrid project that SSAB, LKAB, and Vattenfall initiated earlier this year. The other option is to run more or less business as usual, but to capture the carbon and either utilize the CO2, or in some countries it's popular to think about storage, especially UK, Netherlands, Norway, countries that have good sites for storage. So we are involved in two big research projects focusing on carbon capture, stepwise and Fresme, so I will present them briefly. We have realized the importance of being able to do research on blast furnace gas, so we have invested in a pipeline. On this picture you see the pipeline. This picture is taken from Mefos And here you see SSAB blast furnace. So we have now commissioned a pipeline where we can get blast furnace gas directly from SSAB. So an overview of these two projects. Stepwise came first. It's this part. In stepwise, we take blast furnace gas. We do a reformation of the gas. We use a water gas shift. We do the shift in 2 steps. The second step is a sorption enhanced water gas shift, which means that we take away the CO2 in the same process. So what we really do is that we produce a CO-rich stream and a hydrogen-rich stream. When we had stepwise funded, we didn't really know what to do with these gases. We focused on what happens in these reactors themselves, so we just flare the gases. But then about 1.5 years ago, I started talking to Carbon Recycling International on Iceland. We had a couple of meetings with them, and we then brought a proposal for the Fresno project, which is from residual steel gases to methanol. And the idea about Fresno is then to use the hydrogen-rich stream, the CO2-rich stream, add on some electrolyzer hydrogen, and produce methanol. So, the first project, Stepwise, is the bigger of them. It's a 30 million euro budget, and since this will be demonstrated at Sverige Medfors, we have a very big share of that budget. Some of the partners I can mention here. ECN is a research institute from the Netherlands. They invented this sorption enhanced water gas shift technique. They've been developing it for about 15 years. Johnson Matthey, they produce and develop catalysts for water gas shift reaction. Kizuma Chemicals, they have developed a material that combines water gas shift with CO2 absorption. So what we're going to do, we will demonstrate the combined steam reforming with CO2 separation of blast furnace gas. This is not a new thing to do. The conventional way to do it would be to have a water gas shift in multiple steps. You need to do it at high temperature first, and then you lower the temperature, and you would have the separation to follow. What we do is that you have the first high temperature shift, we then keep the high temperature, and we go into the sorption enhanced shift. So here we separate the carbon dioxide, and since we take away the carbon dioxide, we drive this equilibrium very efficiently to the hydrogen side. So we save process steps, and we can maintain a high temperature. We are building a pilot plant for this that generally looks like this. We have a gas cleaning and a compression of 800 cubic meters per hour. We have gas heaters, heat up to 400 degrees. We have a steam system to add steam to the shift reaction. We have these 2 reactors, and then we flare these 2 products. This plant is under commissioning. We have quite busy days right now. We have the grand opening in September, and the first test will be in October. We then have long duration tests next year. Here you see some pictures. If you can see anything, here's the compression unit for blast furnace gas. Actually, this is the compressor. The rest is just to clean and dry the gas. Here is the water gas shift reactor and the sorption enhanced water gas shift reactor. And to have the size compression, you see a door opening here. So it's a quite big installation. So That brings me to the other project, from residual steel gases to methanol. This started late last year, so we have not yet done very much in the project. It's a bit smaller, but for us it's still very, very important, 4.4 million euro. We will do the demonstration once again at our premises. We have kept some of the partners from Stepwise into Fresme and added some new ones. CRI, of course, that provide the methanol technology, and also Stena Rederi, because we will demonstrate this methanol in Germany. Okay. So what we will do, we will use the existing Stepwise equipment that you just saw on picture. CRI, they will bring in existing methanol skids that they use in another European project. What we will add in Fresme is some treatment of the gas. It's drying. We have guard beds to remove sulfur components, for example, and a membrane system to separate the nitrogen from the hydrogen. We will also bring in an electrolyzer to chip in some extra hydrogen. How much time do you have?
Like 10 minutes to talk?
10?
Yeah.
I'm moving too fast. Okay, then we can take it easy. So, we have just been working for about half a year in this project, so we are currently in the basic engineering work package. We will do the risk analysis in October and then start procurement in beginning of next year. So far we have a 3-plot plan. The Stepwise plant that you just saw is located in this building, which is this red one. We have an 8X building available here, where we will have the membrane system and the electrolyzer unit. These two skids are the ones that CRI will supply. They have the methanol reactor in one of them, and they have a compression skid to increase the pressure for the synthesis.
Sorry, what's a compressor skid?
Skid is just that it's skid-based design. So they have compressors located. It's like a container.
Okay.
So they can easily move it from the other project they are running. They can move it to Sweden for this project. You can also see here we have this flare that we use for Stepwise. But when we're on Fresme, we will take care of gases to produce methanol instead. So, in Fresme, we will operate that pilot for a total of 3 months. The second half of 2019 we will start. Partly dependent on that we have to finish Stepwise before we come into Fresme. We will test different modes of operation, and in the end we will send the methanol that we have produced here to Gothenburg. So we plan to have the final project meeting on board Germanica. One reason that we do these different modes is that the hydrogen from the electrolyzer is very pure, whereas the hydrogen coming from the blast furnace gas, even though we take it through different stages of cleaning, there will still be some trace in there. So we want to test how this affects the catalysts in the process. During the project, we will of course do a full LCA and techno-economic analysis, so we have not really started that yet. we did set up 2 possible scenarios for a full-scale implementation. And this is done for a European reference case, which is a 4-ton per year hot-rolled coil steel plant. That's what we always use as a reference. So if you look at these 2 scenarios, the first one, if we don't use an electrolyzer at all, we take 20% of the blast furnace gas, we will produce 140,000 tons of methanol, which is good.
Will there be any left for GreenPilot?
There might be some leftover, yes. On the other hand, we don't really reduce the CO2 emissions that much because we only take 3.7% of the total content. If you look at the second scenario, when we ship in hydrogen using electrolyzer, we get the better utilization of the CO2 and then of course a higher production of methanol. I have also tried to translate this into SSAB steel plants size in rough numbers. So this means that we could reduce CO2 by about 10% for the second scenario. We would then take 35% of the blast furnace gas. I think that was my last slide. Yes.
Do we have any questions, Magnus?
I have one question
Yep.
concerning this methanol production plant. I guess one of the last step in the process is to separate the methanol from the water.
Yes.
Is it very much integrated, that part of the process? Or can you actually supply raw methanol as well?
We will produce crude methanol. The distillation will be done off-site. We have a couple of options where we can do it, but we have not decided yet. One of the options is actually to ship it to Iceland and do it there and ship it back. So for demonstration, that can be okay. But it depends on the price. Even Chemrec and PGO can possibly do it if they are in business, then we don't know.
The reason I'm asking is that it might very well be like that Stena is interested to run on raw methanol instead of chemical methanol.
Yeah, not. I don't think raw, because then you have about 50-50 water and methanol. But I think they are okay with 10% water or something, so you don't need to put a lot of effort into removing the water.
So how crude is the crude methanol?
It's equimolar, so it's about 50-50.
We had another question.
No, it was
It was. Anyone else?
Is there a difference in the sulfur content in the methanol produced in your plant and for example biomethanol or produced from natural gas?
We have to remove the sulfur down to ppb levels.
So it's that lower in the
before entering the synthesis.
Okay. Yeah, otherwise you will kill the catalyst. Yeah.
Because if no one else has a question, I have one. You said that you were going to do an LCA and some cost calculations, but do you have any like rough estimate of, is this like a price-worthy solution, and will it be expensive, or is it that you get such a benefit from saying that you reduce the emissions, you just take them and release them a bit later, but it's worth a lot for SSAB?
Yeah. There have been some rough estimates. I don't have the numbers. I know that it is quite expensive. As they counted. I have to come back later.
But would you say it's comparable to the numbers shown like for electric fuels or ish?
Yeah, I mean, it pretty much depends on where you put the plant. So.
Yeah, and I guess it will depend also how you value the CO2 that you utilize,
Yeah.
how much benefit you get for that.
And that's also, I mean, that's also a political thing because the steel plant, they don't reduce their emissions at all. But the fuel itself is counted as fossil free or CO2 free. So SSAB, they don't have much to win to do this actually, but not Stena either because they are not included in the emission trading. So, but I think we all live in the same world, so we have a problem to solve.
But what you're saying is that one needs to find ways of how to make a business case of a good business case, because as of now, it's not really a business case for.
Yeah. It's also, I mean, in other parts of the world, there are hundreds of blast furnaces in the world, and in Luleå, we have a climate where we can use this energy for district heating. In many other places, it's just to produce electricity, so very poor efficiency. There are even some places that don't even have a power plant, but that's extreme. So it's a big source of the chemical that they produce out of blast furnaces.
Okay.
You think when this is up and running in a commercial scale, if it will be labor intensive, or is it pretty much fully automatic?
It will not be labor intensive.
Because I think that's probably see our problem in Iceland, that it's more labor intensive than they thought it should be. So actually the labor cost is not really true.
Oh, yeah, okay. I'm not, that part is kind of CRI's business, we leave that to them, so it's kind of a black box for us. But I mean, the other part is pretty much like running, I mean, they have an oxygen plant next to SSAB, and that they run it unmanned. So I don't think you need a lot of labor to run such a plant.
Good. Then I would say that we will end this session before the coffee break with this, and we will take those thoughts with us during coffee and mingle, and see how the future of transport also reaches out into many different other sectors. And we will meet back here 5 minutes past 4. In 20 minutes plus, we will meet back here. We will gather you.
And you're welcome to take your coffee outside, but don't wander off too far. Yeah.
So